Hello students, let us see the topic today. The topic is principle of inclusion and exclusion. It is very simple principle. With the help of this concept, we may do so many types of IIT-JEE problems related to the permutations and combinations. Let us see the principle. Simple thing. This is actually discussed in 10th class itself. N of A union B is equals to N of A plus N of B minus N of A intersection B. All of you know this formula very well. But the principle of the formula behind the thing you can understand. N of A union B is equals to N of A plus N of B minus N of A intersection B, where A and B are any two sets. What is the inclusion? What is the exclusion here? Let us see by diagrammatically. This is set A. Okay. This is my set B. This is the portion A intersection B. What is B here? This is B. This is my A intersection B. So this is my entire A union B. A union B means all the elements inside of this region. Okay. This is A union B. How to express this one? This is A. This is B. Their common portion is A intersection B. Totally this is called A union B. So N of A union B means number of elements in this A union B. That's all. So I am going to equate this set as follows. This is equivalent to what? As it is, I am taking set A and I am taking this portion only. What is this portion? This is nothing but B minus A. The elements which are belonging to B but not A called B minus A. So I am taking A minus B, A union B as the sum of A and B minus A, like this. Union, this is what? B minus A. The set of all elements which are belong to B, not in A. So we can write A union B as A union B minus A. This is the important thing here. Now I am going to B minus A is rewritten as in terms of B. This is my inclusion. So if I complete this portion, we get B and we are including A intersection B to this one and then immediately exclude. We get one inclusion and one exclusion. We get in this manner. This is equivalent to what? This is the same A union. I am writing what? B. I am writing B. And we have subtract what? A intersection B. Are you understand or not? So instead of B minus A, I am writing B. That means we are adding A intersection B. This is portion. This portion is including. So from here to here, what I have done? Including A intersection B. From here to here, we are adding A intersection B. Once if you add A intersection B, to equate the equality, I am subtracting this A intersection B. Here is inclusion is there, here exclusion is there. One including and one excluding, we compensate the entire equation. So this is the concept related to inclusion and exclusion. So A union B can be written as A union B minus A. This can be written as A union B minus A intersection B. That is A union B in the sense N of A plus N of B minus N of A intersection B. So N of A union B is nothing but number of elements of A plus number of elements of B minus number of elements of A intersection B. So n of A plus n of B. By taking n of A and n of B, we are taking A intersection B 2 times. That is why we are excluding 1 time simply. So this is the concept. N of A union B is equals to n of A plus n of B minus n of A intersection B. Moreover, you see this concept. N of A bar intersection B bar is nothing but A union B whole bar, that is equals to n of U minus n of A union B. So A bar intersection B bar. Intersection means and. A bar means what? Complement of the set A, not A. B bar means what? Not B. The set of all elements which does not contains the elements of B, we obtain one set that is called B bar. That is complement of what? B. This is A bar. This is the complement of A. N of A bar intersection B bar is equivalent to what? N of A union B whole bar. That is nothing but n of U minus n of A union B. U means what? Universal set. How to obtain this one? Let us see by diagrammatically. This is universal set. The entire set is my universal set. Okay. Next, what is this? Set A. The set A. This is my set A. What about the remaining portion? The entire remaining portion is nothing but A bar. Suppose here is one element. This is not belongs to A. That is why this is belongs to what? A bar. So this is my A bar. Understand? This is A and universal set minus A gives what? A bar. This is the relation of A and A bar with respect to the universal set as shown in the figure. Similarly, consider the universal set. This is my set B. Immediately, the remaining portion is what? B bar. This is the portion which does not contain B called B bar. Okay, this is my B bar. Now, how to find A bar intersection B bar? That is the common region to both A bar and B bar. So this is the A bar region. This is B bar region. What you have to get? You have to get the common region for both A bar and B bar. Now let us see this one. This is universal set. This is my set A. This is my set B. So what is the A bar intersection B bar? The values which contains the portion does not having A and B. So this is the portion. This is the portion does not contains the values or terms of A and B like that. So this is the region. What is the region as shown in the figure? That is yellow shape. That is A bar intersection B bar. A bar means this is the portion. Okay, pink portion. This is the B bar, green portion. So in this third figure, the yellow portion is what? A bar intersection B bar. This is A bar intersection B bar. It is equivalent to what? This is the set does not contain A union B. That is why we call it as A union B whole bar. A union B whole bar. So both the sets are equal. A bar intersection B bar is equivalent to my A union B whole bar. That is why the number of elements must and should be equal. Hence, n of A bar intersection B bar is equals to n of A union B whole bar. That is nothing but number of elements in the universal set minus n of A union B. This is also very important concept related to above concept. So this gives what? This is the relation between A bar and B bar to A and B. So left hand side is in terms of intersection, right hand side is in terms of union. A bar intersection B bar means neither A nor B, not happening of set A as well as not happening of B, which is equivalent to what? Total number of elements. Total number of elements means the number of elements in the universal set minus n of A union B. N of A union B. This is the relation between A bar B bar to A and B. This is called De Morgan's law. With the help of these simple two tools, we can solve so many problems related to JEE mains as well as advanced, like derangements as well as a number of ways of distributing and different things into the or different persons or objects like that. Okay. In the same manner, we can extend this concept. This is what? A bar intersection B bar. Extend the concept to 3 sets, that is n of A union B union C, that is equals to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of C intersection A plus n of A intersection B intersection C. In the above manner, we including and excluding concept, we will get the above result. So similarly, n of A bar intersection B bar intersection C bar is nothing but n of A union B union C whole bar by De Morgan's law. This is equivalent to what? N of U minus n of A union B union C. Understand? So this is for 3 elements, n of A union B union C. So individuals plus, by taking 2 elements minus, by taking 3 elements plus. So plus minus plus will be alternatively come. So for A union B union C, let us see the diagram. This is universal set. This is my A. This is my set B. This is my set C. So A, B, C are the 3 sets. They intersecting as shown in the figure. So what is this A? This is entire A. This is my B. This is C. So what is this portion? A intersection B. What is this portion? A intersection C. What is this portion? B intersection C. How to get this one? Just I will explain to you. This is A union B union C. So this is the entire portion related to A union B union C. Am I correct or not? I am taking A union B. This is A union B. Okay. This portion is nothing but n of A plus n of B minus n of A intersection B by above theorem, by above relation. So n of A plus n of B minus n of A intersection B. This is n of A, this is n of B minus n of A intersection B. For A and B, this is A union B. I am taking this one also for C. For C, I am including C here. So A union B union C. When I am including C, what are written extra? The extra things are A intersection C and the B intersection C. So we have to include C in this set. I am going to exclude these 2 things. When I am excluding those 2 things, that is A intersection C as well as B intersection C, I write here this is minus A intersection C, this is my B intersection C. We are subtracting A intersection B intersection C 2 times. That is why you have to include one more time. That is why I am writing plus. That is why I am writing plus A intersection B intersection C. That is why we get A union B union C as A union B union C minus A intersection B minus B intersection C minus C intersection A plus A intersection B intersection C. That is why n of A union B union C as sigma n of A minus sigma n of A intersection B plus sigma n of A intersection B intersection C. In the same manner, we can write the De Morgan's law for the 3 sets. N of A bar intersection B bar intersection C bar as n of A union B union C, that is equals to n of universal set minus n of A union B union C. Right. So we can expand the same phenomena in this manner. N of A1 union, A2 union, A3 union and so on up to An is what? This is the extension of the inclusion and exclusion concept. So I am writing in this manner sigma n of A minus sigma n of Ai intersection Aj. So I and J lies between 1 to n. So first I am taking the individual sets and taking 2 sets and next take 3 sets and so on up to taking all the sets. So the entire principle is depend upon the first case, like n of A union B is what? N of A plus n of B minus n of A intersection B. How it happened? We are including A intersection B to B minus A and excluding A intersection B. That is why we obtain n of A plus n of B minus n of A intersection B. One inclusion and one exclusion of A intersection B, we obtain the above result. In the same manner, we have to add some sets and subtract the same sets to the expansions. We obtain these relations. That's why n of A1 union A2 union and so on up to An is obtained in this manner. So this is for the set of all single sets. This is the intersection of the two sets. This is intersection of the three sets and so on by taking all the sets. So minus and plus or minus alternatively will happen. This is very important result to use the problems related to JEE Advanced to the relation between the things what we have discussed earlier. They are called one is derangements and other one is distribution of things and different things to the objects, like that. Understand? So n of A1 union A2 union and so on up to An as in this manner. Okay. Next, what is the range of I? 1 less than or equal to I less than or equal to n and I not equals to z. Similarly, n of A1 bar intersection A2 bar intersection A3 bar and so on up to An bar is what? By De Morgan's law, n of A1 union A2 union A3 and so on up to union An whole bar, that is nothing but n of u minus n of A1 union A2 union and so on up to An. This is the relation between the conjugates to the real sets. A complement. This is A1 complement. This is A2 complement. A1 complement is obtained by the universal set minus A1. A2 complement is obtained by the universal set minus A2. So this is the relation between AI bars to AIs. This is the logic. So suppose if you want to get neither A1 nor A2 nor A3 and so on nor An is obtained by n of universal set minus n of any one of the happening, any one of the set happening. So n of u minus n of A1 union A2 union and so on up to An. This means what? Left side means what? n of A1 bar intersection A2 bar and so on up to An bar means what? None of the set will happen. None of the elements which does not contained in A1, A2, A3 and so on up to An. With respect to set sense. With respect to event sense, none of the event A1, A2, A3 and so on up to An will happen. Neither A1 nor A2 nor A3 and so on up to nor An. That is the meaning. Okay. By using the above principle, we can find derangements. Already we discussed the importance of this topic, and distribution of n different objects in r different boxes if each box at least one object is presented. Each box should get at least one object. So these are very two important applications by using the inclusion and exclusion concept. One is derangements and other one is the distribution of different things, not like things, different things to the different objects. Very important. Let us see how the application is, how the applications are moving by using the principle. Derangements. See this one. I can explain the dearrangement through one example. See this, the result. There are n letters and n corresponding envelopes. How many letters are there? N letters are there. How many corresponding envelopes are there? N envelopes are there. I mean what? One letter goes to one envelope. One correspondence. Okay, there are n letters and n corresponding envelopes are there. Now, my result is, see here, the number of ways, listen carefully, the number of ways in which the letters can be placed in the envelopes. The letters goes to envelopes. One letter in each envelope. Don't confuse, one letter is going to the one envelope exactly. So that no letter is placed in the correct envelope is something. That is n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on up to plus minus 1 whole power n by n factorial. With the above simple phenomena, simple result, simple concept, we are going to do this big shot. This is the dearrangement. So see the logic, how it is the logic behind to apply the dearrangements. See here, there are n letters are there, n envelopes are there. So we can put the n letters in n envelopes correctly in only one way. Am I correct or not? First letter go to first corresponding envelope, second letter go to second corresponding envelope. In the same manner, nth letter goes to nth envelope in only one way. In only one way. Listen carefully. But they are asking dearrangements. That means the number of ways in which the letters can be placed in the envelopes so that no letter going to the correct envelope. No letter going to the correct envelope. See here, remember one thing. Total minus all letters goes to correct is not correct answer. This is not correct answer. This is not the complement to our question. This is not the complement to our question. Our question is what? We have to dearrange such a way that no letter go to correct envelope. No letter go to correct envelope. That means total minus all are go to correct. Is it correct? No, that is not correct. So we have to proceed. How to proceed is the very, very important. What is the logic behind this question? How to use the how to use the above concept like inclusion and exclusion concept. So in this problem, no letter go to correct envelope. No letter go to correct envelope. Keep this sentence in your mind. So let us see my game plan. These are my envelopes like this. 1, 2, 3, 4 and so on up to n. Their corresponding letters are like this. 1, 2, 3, 4, 5 and so on up to n. There are n letters, n envelopes are there. What is my target? No letter go to its corresponding envelope. Now I am trying to show one of the dearrangement of my total arrangements, dearrangements. Dearrangement means this is letter 1. It doesn't go to envelope 1. So this may go to either 2 or 3 or 4 or nth letter. So similarly the second letter does not go to the second envelope. This may go into the remaining n minus 1 envelopes. In the same manner we can send fifth letter to 1, 2, 3, 4 except 5 and up to n. So these are all dearrangements. Out of all these dearrangements, I am going to show one dearrangement as shown in the figure like this. This is letter 1. I am sending to fifth envelope. This is second letter. Send into third envelope. This is my third letter. Send into nth envelope. This is my fourth letter. Go to first envelope. This is my fifth envelope. Fifth chord, goes to the second envelope. In the same manner, nth letter goes to my fourth envelope. In this manner, we can send the letters so as to no letter go to the correct envelope. Am I correct or not? All the letters goes into the wrong envelopes. So this is one of the possibility. This is the one of my possibility. So this type of possibilities are how many? This type of possibilities are how many? This is my question. Understand? So no letter go to its correct envelope. For that is why I am going to construct some events and how to face this problem. Let us see the game plan. N letters are denoted by 1, 2, 3 and so on up to n. These are my n letters. 1, 2, 3, 4 and so on up to my n letters. This is the first step. Very, very, very important construction point. That is, let AI denoted by the set of distribution of letters in envelopes. One letter in one envelope so that ith letter is placed in the corresponding envelope. What is my AI? This is one set. Its set consists of what? all the distributions, all of my distribution. Which type of distributions? The letters are distributed to the envelopes such that your ith letter goes into the ith exact envelope. Ith letter goes to its exact envelope. What about the remaining? Some may be go correct, some may be go wrong. Remaining all of them are go wrong, whatever it may be. But my ith letter goes to correct envelope. That is my set. What is AI? AI is the set which consists all the distributions, all possible distributions, such that the letter AI goes to the correct envelope. The letter AI goes to the correct envelope. What about A1? What about A2? What about A3? What about AI minus 1? And so on. What about AN? I don't know. Some of them go to correct, some of may go to wrong. That is, don't bother about. AI is my set like that. So what is A1? A1 is set. It consists of all distribution of letters in envelopes so that my first letter go to correct envelope. The remaining are whatever it may be. That is the basic concept to prove this proof. Okay. Now, what is n of AI? My first question is what? N of AI is what? Number of elements in that set AI is what? So, what is my set here? In each and every possibility, my AI letter goes to correct address. How many ways it goes to correct address? Only one way. Letter AI has corresponding one envelope, that is, say AI dash say, that goes to only one way. Letter AI goes to its correct envelope in only one way. How many remaining letters are there? How many remaining envelopes are there? That is my question. The remaining letters are n-1. The remaining envelopes are n-1. How many ways we can arrange the letters in envelopes? n-1 factorial ways. Am I correct or not? Take the first letter, substitute in any one of n-1 places, that is n-1 ways. Take the second letter, we can put the n-2 places in n-2 ways. So n-1 into n-2 and so on up to one way. That is nothing but n-1 factor. What is this one? This one is nothing but the number of ways of arranging the letter AI into its correct envelope. That is only one way. It has correct. So n of AI is equals to n-1 factorial into 1. That is simply n-1 factorial. Again, A of I intersection AJ. This is the set. What is this? AI intersection AJ represents set of distributions of letters in envelopes such that ith and jth letters placed in their correct envelopes. Ith letter go to correct envelope as well as jth letter go to correct envelope. In the above case, what? Just AIth letter go to the correct envelope. AI means I runs from where to where? 1 to n. A1 is also n-1 factorial. A2 is also 1 into n-1 factorial. n-1 factorial. An is also, n of an contains also n-1 factorial of the elements. See here, AI intersection AJ is the another set which consists of all distributions. All the set, this is the set which consists of what? All of the distributions of what? Letters to what? Envelopes, such a way that the ith letter and jth letter is placed in their corresponding envelopes, right? Correct answering envelopes. That is how many ways? See here, n of AI intersection AJ nothing but number of elements in AI intersection AJ. That is what? 1 into 1 into n-2 factorial. How it is happen? AI goes to its corresponding envelope in one way. AJ letter goes to corresponding envelope in one way. And remaining letters are how many? n-2 letters. How many remaining envelopes? n-2 remaining envelopes. So these n-2 letters can be put in n-2 envelopes in how many ways? n-2 factorial ways. Which letter may be go to any of the n-2 remaining envelopes. That is in 1 into 1 into n-2 factorial. That is n-2 factorial ways. Can you say what about n of AI intersection AJ intersection AK for 3? You can easily told 1 into 1 into 1 into n-3 factorial. Am I correct or not? In the same manner, I can write this one. N of ai intersection aj intersection ak 1 into 1 into 1 into n minus 3 factorial. So ai go to one way, aj goes to one way, ak goes to one way. Because ai, aj, ak are the three letters, they are goes to the correct envelopes. The remaining may be go whatever it may be. Sum of may go to correct, sum of may go to wrong. That is why we are taking it as n minus 3 factorial. So can I extend up to n or not? So n of ai intersection aj intersection and so on up to ak is what? 1 into 1 into 1 and so on up to 1. That is nothing but 1. Keep one side. Now this is the important step. Hence, what is your required number? N of a bar intersection a2 bar intersection and so on up to an bar. Am I correct or not? What is a1 bar? a1 bar is the complement of a1. Am I correct or not? Complement of a1. Listen very carefully. What is a1 bar? That is the complement of a1. What is your a1? a1 is the set of all distributions such that the letter a1 goes to corresponding envelope, corresponding right envelope. So a1 bar means what? The set of all. It is the set which consists all the distributions such that a1 does not go to what? a1 does not go to its corresponding envelope. a1 does not goes to its corresponding envelope. I mean the remaining. What about remaining? You don't know. You don't know about its remaining. Some of may go to correct, some of may go to wrong. But a1 bar consists the set of distributions so that the letter, first letter, that is the letter 1, does not go to its corresponding right envelope. Am I correct? Similarly, what about a2 bar? a2 bar is the complement of a2. What is a2 bar? Complement of a2. What is a2? The set of all distributions such that the letter a2 goes to its corresponding envelope. a2 bar means what? The set of all distributions such that the letter a2 does not go to its corresponding envelope. That means what? The remaining letters, in that case, some of them go to correct, some of them go to wrong. In the same manner, a3 means what? The set which consists all the distributions such that the letter a3 does not goes to its corresponding envelope. So a1 bar, a2 bar, a3 bar and so on an bar. Each set has one speciality. What is the speciality? The corresponding letter does not goes to its corresponding envelope. What is my an bar? An bar is the set of all distributions in which what? Set of all distributions in which the letter an does not goes to its corresponding envelope. What about a1, a2 and so on up to an? Some of the letters may go to right or go to wrong. Whatever it may be, an bar is the set of all distributions in which the letter an does not go to my corresponding right envelope. So if you collect all these sets and take their intersection, what do you get? What do you get? You get no letter go to its corresponding envelope. Am I correct or not? This is a1 in which my first letter does not go to correct envelope. The remaining whatever it may be. In a2 bar, my letter a2 does not go to its correct envelope. What about a3 bar? My letter a3 does not go to its correct envelope. What about an bar? My letter an does not go to its corresponding nth envelope. Right? So all these intersections gives what? No letter go to its corresponding envelope. That is why you need to find n of a1 bar intersection, a2 bar intersection, a3 bar intersection and so on up to an bar. This is your target. It is equivalent to what? Your 80% of the job is completed. So this is equivalent to n of a1 bar union, a2 bar union and so on up to an bar by above De Morgan's law. How to write this one? This is nothing but n of u, number of elements of the universal set, that is the total number of possibilities, minus n of a1 union, a2 union and so on up to an. Here we have to use the inclusion and exclusion concept. So this is the way to applying my inclusion and exclusion concept to this large problem. See how the trick is applied here. You can enjoy this one. Okay, now this is n of u is nothing but what? N factor. How it is happen? There are n letters, n envelopes. how many ways we can arrange them? N factorial ways. The first letter may go in n ways, second letter may go to n minus 1 ways, and so on up to nth letter go to 1 way. Total number of ways by Mn rule, n into n minus 1 into n minus 2 and so on up to 1, that is nothing but n factorial. This is my n of u universal set elements, number of elements in my total universal set, that is n factorial. So this is n of a1 union a2 union and so on up to an. This is the definition by inclusion and exclusion. Sigma n of ai intersection aj plus sigma n of ai intersection aj intersection ak and so on up to plus n of ai intersection a1 intersection a2 intersection and so on up to an. So how to obtain this n of ai? What is n of ai? Number of elements in ai. Once if you define the set, you don't forget what is ai. AI is the set which contains all the distributions such that ith letter goes to its correct envelope. Ith letter goes to its correct envelope. How many ways this can be done? 1 into n minus 1 factorial. For first letter, 1 into n minus 1 factorial. For second letter, 1 into n minus 1 factorial and so on. So in this manner, we can get like this. N factorial minus NC1, I am writing NC1. Why I am writing NC1? You have n letters. We select one set like that NC1 ways. We have to select one set in NC1 ways. One set in the sense, one letter say NC1 ways. And in each case, we have n minus 1 factorial arrangements. What is A1? A1 is the set of all distributions such that A1, letter A1 goes to correct envelope. A1 is set. A1 is also taken as my first letter. Don't feel otherwise. What is, I repeat once again, A1 is what? A1 is the set which consists all distributions such that my letter A1 go to correct envelope. So this is NC1. How it happened? We are selecting one letter from n letters which is goes to correct address. That is, we can select in NC1 ways. We have to select in NC1 ways. Either first letter or second letter or third letter or nth letter. NC1 is the number of ways of selecting the letter which is goes to correct way. The remaining are goes to what? N minus 1 factorial ways. So n of a1 is what? N minus 1 factorial. N of a2 is what? N minus 1 factorial. N of a3 is what? N minus 1 factorial. In this way, sigma n of a is what? NC1 into n minus 1 factorial way. Similarly, how many ways we can choose ai intersection aj's? How many ways we can choose? How many sets are there? A1, A2, A3 and so on up to an sets. How many ways we can choose two different sets I not equal to j? NC2 ways. For each set, how many arrangements are there? N minus 2 factorial. Arrangements, I mean distributions. In each case, we have n minus 2 distributions. Select two sets. Selection of two sets in the here. AI intersection AJ means this is the set which consists all the distributions such that the letter AI and AJ go to correct envelopes. Suppose A1 intersection A2, that means what? The set of all distributions in which A1 and A2 go to correct envelopes. So in this manner, how many sets are obtained? NC2 sets are obtained. In each case, how many distributions are there? N minus 2 factorial distributions. By Mn rule, total number of ways is how much? NC2 into n minus 2 factorial. Similarly, how many ways we can select these three sets out of n sets? NC3 ways. In each case, how many arrangements are there? N minus 3 factorial ways. Why n minus 3 factorial? 1 into 1 into 1 into n minus 3 factorial. Already we proved. So in the same manner and so on up to plus minus 1 whole power n minus 1 into NCn into 1. Why I am writing 1? All the letters goes to correct envelopes. So we select NC1. We are selecting all the letters at one time. N letters are selected at a time is NCN ways. All the letters goes to right way in one way. Am I correct or not? This is 1. So this is NC1 into n minus 1 factorial minus NC2 into n minus 2 factorial plus NC3 into n minus 3 factorial and so on. And by simplification, we get in this manner. n factorial minus n into n minus 1 factorial. NC1 is nothing but n. NC2 is nothing but n into n minus 1 by 2 factorial. NC3 is nothing but n into n minus 1 into n minus 2 by 3 factorial, and so on. So n into n minus 1 into n minus 2 factorial is nothing but n factorial. n into n minus 1 into n minus 2 into n minus 3 factorial is nothing but n factorial, and so on. This one can be written as n factorial by n factorial. See this in this manner, n factorial minus n into n factorial, n minus 1 factorial is n factorial, and so on, like that. Minus 1 whole power n minus 1 into n factorial by n factorial. Taking n factorial common, we get n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, and so on up to plus minus 1 whole to the power of n into 1 by n factorial. This is the way to derive the required thing. Understand? Here the important concept is you have to take AI. You have to take AI. What is your AI? AI denotes the set. Set. In set, what are there? In set, elements are there. What are the elements here? Distribution. One distribution is one element. What is the distribution? Distribution of letters to what? Envelopes, such that your letter AI goes to correct envelope. That is the definition of my AI. Once if you define my AI like that, we can find n of AI, A1 intersection, A1 bar intersection, A2 bar intersection, and so on up to an bar. This is my target. N of A1 bar, n of A1 union, A2 union, and so on up to an. That is, this is value. This is equivalent to this one, and this is equivalent to this one. This is my inclusion and exclusion concept I am applying here. So how we are getting NC2 here? We are taking two sets out of n sets in NC2 ways. In each case, we have n minus 2 arrangements, n minus 2 factorial arrangements. Okay. This is the formula. With the formula, we can do one problem. So your number of letters are 4 and 4 envelopes are there. How many ways we can send the letters to the envelope such that no letter go to its corresponding envelope? How many ways? What is n here? 4. Simply 4 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. On simplifying, you get it is 9 ways. 4 factorial into 12 minus 4 plus 1 by 4 factorial. 4 factorial gets cancelled. 8 plus 1, 9 ways. Simply, we can, once if you have the derivation, it is very easy to write the answer. So this is the way to write the derangements by using inclusion and exclusion concept. Okay, let us see this one. Note, suppose out of n letters, if you want to send r letters goes to wrong envelopes, then the number of ways is what? NPR into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, and so on up to plus minus 1 whole to the power of r into 1 by r factorial. How it happened? Here all the letters are not goes to the wrong envelopes. Here exactly r letters are go to wrong envelopes. Exactly r letters goes to wrong envelopes. You have to select r letters which are goes to wrong first of all. How many ways this can be selected? NCR ways. NCR. So r letters are there. R letters and r envelopes. You have to send them in the wrong way. In how many ways? 1 NPR, r factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus and so on up to plus minus 1 whole power r into 1 by r factorial. That is what? NCR into r factorial. This is my derangements for r letters and r envelopes. This is my dearrangement. Into NCR. How it is obtained NCR? We are selecting r letters out of n letters, NCR ways, and these r letters goes to wrong envelopes. So r factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus and so on up to minus 1 whole to the power of r into 1 by r factorial. What is my NCR into r factorial? This is nothing but NPR. Am I correct or not? So NPR into 1 minus 1 by 1 factorial plus and so on up to minus 1 whole power r into 1 by r factorial. Suppose 5 letters and 5 envelopes are there. Exactly 3 letters goes to wrong. How many ways we can send them? So 5p3 into This is the answer. 5p3 into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. On simplifying, it is 20 ways. 5 factorial by 2 factorial. What is n PR? N factorial by n minus r factorial. That is 5 factorial by 2 factorial into 1 gets cancel. 1 by 2 minus 1 by 6, that is 3 minus 1 by 6. So 20 ways. The required number of ways is 20. Okay. Now let us see the another application. Before going to see the another application, see this problem. This is given in JEE Advanced 2014. 6 cards are there, 6 envelopes are there, are numbered 1, 2, 3, 4, 5, 6 and so on. Sorry, 5, 6 up to 6. Or the cards are to be placed in envelopes so that each envelope contains exactly 1 card and no card is placed in the envelope bearing the same number, and moreover the card number is 1 always placed in the envelope number 2. Then the number of derangements is dash. This is the question. See here, this is the question given in JEE Advanced 2014. Already we discussed 90% of the concept previously, and one more extra thing is added here. What is the thing here? The number 1 always placed in the envelope 2. This is also wrong message, wrong envelopes concept, but it is given clearly. The number 1 goes to what? Envelope 2. Okay, this is also wrong arrangement. Okay, 1 goes to 1, that is the correct arrangement. But this is, even though this is wrong arrangement, they are given to you. My letter 1 should be goes to envelope 2. They are mentioned. That is why a little bit of the modification is there in my conditions. Okay, one condition is added to you. So 6 letters are there, 6 envelopes are there. Can you find the total number of derangements or not? By the above problem, we can find the derangements. 6 cards are there, 6 envelopes are there. They are numbered so that each envelope contains exactly 1 card. No card is placed in the envelope such that the number 1 is placed in the envelope 2. Then the number of derangements is what? That is my question. Okay. So the total number of derangements is 6 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus 1 by 5 factorial plus 1 by 6 factorial. Up to here, no doubt. Because we proved this one. N factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on up to plus minus 1 whole to the power of n into 1 by n factorial. In the same manner, we applied the formula like this. But what is the given extra condition here? Number 1 always placed in the envelope number 2. That is the condition. With my condition, the number of possibilities are increased or decreased. This is the total number of possibilities. This is the total number of possibilities. In the total number of possibilities, we have some of the possibilities satisfies this condition only. What is my condition? Number 1 goes to envelope 2. Number 1 goes to envelope 2. Here, these are all possibilities. In all of my possibilities, the number 1 goes to either 2, or 3, or 4, or 5, or 6. So, how many possibilities are? This is the total number of possibilities, 265. But my letter 1 may goes to 2, or 3, or 4, or 5, or 6. So, how many times you have to reduce? 1, 2, 3, 4, 5 times you have to reduce. 6 factorial into something, that is the value 265. 265 is the total number of ways. Total number of ways. In this case, my 1 goes to 2 or 3 or 4 or 5 or 6, whatever it may be. But what they are asking, my 1 goes to envelope 2. So 5 times of the above thing should be reduced. So you have to divide it by 5. So the number of ways is what? 265 by 5, that is 53 ways. So what is the condition here? My letter 1 goes to number 2. So the conditions are more, the number of possibilities are less. Total number of possibilities without my condition is 265. So in this case, my 1 goes to either second envelope or third envelope or and so on up to sixth envelope. But they are given that my 1 goes to second envelope. So 5 times of the required things should be reduced. That is why 265 by 5. So 53 ways is the correct answer. Understand? Now see the next application related to the above concept, inclusion and exclusion, distribution of n different objects into r distinct boxes if in each box at least one object is placed. So our principle is very simple. We are solving the different difficult problems related to JEE mains as well as advanced. Distribution of n different things. The things are different. The boxes are also different. How many ways we can distribute them into the boxes such that each box gets at least one object. Each box gets at least one object. No box should be empty. Note that no box should be empty. Suppose you have 20 different objects and 4 boxes are there. How many ways can you distribute? This is very big task for you. Suppose 3 things are there, 2 boxes are there. How many ways you can distribute? 2, 1, 1, 2. First box assign 2 balls and second box can assign to 1 ball. 2, 1 and 1, 2. These are 2 ways. This is simple problem you can solve. Suppose I have 100 different things and 40 different boxes are there. How many ways can you distribute means? You can't move without my logic. So this type of problems are also solved by my inclusion and exclusion concept. So in the same manner, I am going to define some sets and see how is my game plan. There are n distinct objects are there and r distinct boxes are there as shown in the figure like this. These are balls, objects. My objects are taken as balls like that. Here I am showing 1, 2, 3, 4, 5, 6 balls. You take it as n distinct objects and my boxes are like this. Some of the boxes are large, some are short. Even though the capacity of box is it takes all the balls and given condition is each box consists of at least one object. At least one object. Don't forget your given conditions. Understand? There are n distinct objects and r distinct boxes are there as shown in the figure. So what is your target? You have to distribute all the balls into all the boxes so that no box is empty. No box is empty. Note that the capacity of each box may take any number of the balls. Each box may take any number of the balls. So I am going to show one of the distribution to you. So you are going to distribute the balls to what? Boxes. So that no box is empty. See, listen carefully. See one of the distribution. These are the balls 1 and 3 as shown in the figure 1 and 3. 1 and 3 balls goes to one of the box as shown in the figure. This is the ball goes to the third box. In the same manner that ball is also go to the third box. Understand? This is one thing. Next, this is my first ball. I am going to assign the ball to the last box. Similarly, this is my last ball, nth ball say. I am going to distribute this ball to second box. In the same manner, take the last 2 balls. I am going to assign these balls to my first box. Am I correct or not? This is the one of the distribution. This is my one of the distribution. So how many such type of distributions are there you are going to find out. This is very difficult without knowing logic. Am I correct or not? We have n different things, or different boxes, or different persons. You are going to distribute the n different things to r different persons or different boxes. You have some logic. So the logic behind this concept is my inclusion and exclusion concept. Before going to apply directly inclusion and exclusion concept, you have to define the sets logically. You have to define the sets logically. Are distinct boxes such that at least one box is at least one object placed. This is the thing. This is my interesting thing. At least one object placed. That means no box should be empty. No box should be empty. That is why I am going to define sets like this. This is the first step. Very, very important step. With the help of this step, we can finish the problem. What is my AI? AI is the set. AI is the set. Understand the step. AI is the set. It consists of what? Elements. What are the elements here? Each element is equal to each distribution. What is my distribution? Distribution of objects. Objects are n objects. If ith box get no object. Ith box no object. Is it reverse of my concept or thought or not? This is AI. It is not followed my concept. AI is the set. I am defining in this manner. This doesn't follows my concept. What is that? At least one object placed. This set overcomes my statement. That is, in this manner I have to choose the sets. In this manner I have to choose my sets. In the previous concept also we have choose the sets like this. So what is AI? AI is the set of all distributions in which ith box is empty. Ith box is empty means ith box has no object. What about my AI bar? AI bar is the set of all distributions such that ith box has object. Ith box has at least one object. Ith box has at least one object. What about remain? I don't know. What about remaining boxes? I don't know. But AI bar is the set of distributions in which AI consists at least one object. At least one object. That is the logic. Similarly, what is my A1? A1 is the set of all distributions of objects in which first box gets no object. In this manner, we have to define the sets. Now we play the game. What is n of ai? What is n of ai? R minus 1 whole to the power of n. How it is happened? Here, ith box does not contain no object. That means what? All the n object goes to remaining r minus 1 boxes. Am I correct or not? So, A is the box. It doesn't agree to take any one of the ball out of n balls. It is closed. It is closed. That is why we have to send n balls to my r minus 1 remaining boxes. So, first ball, how many ways can you send? R minus 1 ways. Second ball, how many ways can you send? R minus 1 ways. Note that the box may take any number of balls. We already discussed it. Here repetition is allowed. So first box may send in R minus 1 ways. Second ball may send in R minus 1 ways. Third ball may send in R minus 1 ways, and so on up to nth ball may send in R minus 1 ways. Because ith box doesn't interested to take any ball. So n of ai is equals to r minus 1 whole to the power of n. Similarly, n of a1 is r minus 1 whole power n or not? A1 is a set which consists of all distributions such that the first box doesn't take any of the ball. The first box is empty. The first box is empty. It rules out my condition. So that type of sets I am taking here. That is the logic. Please listen. A is the set of all distributions of objects if ith box gets no object. So n of A is nothing but r minus 1 whole to the power of n. Similarly, n of ai intersection aj is equals to r minus 2 whole to the power of n. Am I correct or not? Ai intersection aj means what from my condition? Both ai and aj boxes do not agree to take any ball. Do not agree to any ball. That means all the balls goes to remaining r minus 2 boxes. So first ball may be going r minus 2 ways. Second ball also may be going r minus 2 ways. And also nth ball may be going r minus 2 ways. So the number of ways is r minus 2 whole to the power of n. Now tell me, what about n of ai intersection aj intersection ak? r minus 3 whole to the power of n. R minus 3 whole to the power of n. See here, that is n of ai intersection aj intersection ak is r minus 3 whole power n. Can you proceed in the same manner or not? So the required number of ways is I am writing n of a1 bar intersection, a2 bar intersection and so on up to ar bar intersection. Same model. Am I correct or not? What is a1? a1 is the set of all distributions so that first box is empty. A1 bar means what? The set of all distributions. This is a set which consists of all distributions in which A1 is not empty. The set A1 is not empty. What about remaining sets? I don't know. Whatever it may be. Some may be filled, some may not be filled. What is A2 bar? A2 bar is the set which consists all distributions such that A2 box A2 contains at least one ball. Box A2 contains at least one ball. Similarly, what about AR bar? AR bar is the set of all distributions in which box AR contains at least one ball. At least one ball, because AR is what? It doesn't. AR is the set of all distributions in which box AR doesn't take any ball. Its complement means it takes at least one ball. At least one ball. That is my target. So if you take all of their intersection, A1 bar means what? A1 contains at least one element. A2 bar means what? It contains at least one ball. AR bar means what? Box R contains at least one ball. If you take all of their intersection, what you get? You get the distribution of all the balls to the boxes so that no box remains empty. That is the entire logic. So it is equivalent to what previously we discussed, n of u minus n of a1 union a2 union and so on up to an. This is nothing but r power n. N of u is nothing but r power n. How it is happen? You have n balls. You are going to send the n balls to the r boxes. Whatever it may be, r power n ways. Because take the first ball, you may allot it to the any one of the r boxes in how many ways? R ways. Second ball can be allotted to r ways. Third ball can be allotted to r ways, and so on. Nth ball can be allotted to r ways. R into r into r and so on up to n ways. That is r power n. Total number of ways is r power n minus, this is the old formula. This is my inclusion and exclusion concept. A1, AI intersection AJ, AI intersection AJ intersection AK, this is AK, and so on up to plus minus 1 whole power r minus 1 into sigma n of A1 intersection A2 intersection and so on here. Already we discussed how many n of AIs are there, n of AI intersection AJ is how many, like that. So already we discussed each and everything. What is the value here now? This is r power n minus rc1 into r minus 1 whole to the power of n. So n of ai, how many boxes are there? R boxes are there. How many ways we can select one box from out of r boxes? rc1. That box is empty. What is my selected box? The selected box is empty box. That means that is not allowed to take any ball. How many remaining boxes are there? R minus 1 boxes. These R minus 1 boxes are filled with n balls. This can be done in R minus 1 whole to the power of n ways. Already we discussed this one, how we are getting. So RC1 into R minus 1 whole to the power of n. This is RC2. How it is obtained RC2? How many boxes are there? R boxes. Out of R boxes, how many ways? Select two different boxes. This is in RC2 ways. RC2 ways. These two boxes are not agreed to take any of the ball. That is, two empty boxes are selected out of R boxes in RC2 ways. The remaining boxes are n minus 2. We have to send the n different balls to the R minus 2 boxes in R minus 2 whole to the power of n. So the number of ways is RC2 into R minus 2 whole to the power of n. In the same manner we proceed in this get RC3 into R minus 3 whole power n plus and so on up to minus 1 whole power R minus 1 into RC R minus 1 into 1. Okay, so on simplifying this one, r power n minus rc1 into r minus 1 whole power n plus rc2 into r minus 2 whole power n and so on up to plus minus 1 whole to the power of r into rc r minus 1. This is the second application for the inclusion and exclusion. So what is here? There are n different objects are there and are different boxes or persons, whatever it may be there. So we are distributing n different things to r different persons or r different boxes in this manner. This is also equivalent to number of onto functions. Number of onto functions from set A to B. A contains n elements and B contains r elements. Onto function means range is equals to codomain, because every element of codomain has at least one pre-image. That is why no element should be empty. No element should be empty, I mean no element doesn't have pre-image. No element doesn't have pre-image. That means what? Every element has at least one pre-image. That is why this is the number of onto functions background. R power n minus rc1 into r minus 1 whole power n plus rc2 into r minus 2 whole power n minus rc3 into r minus 3 whole power n and so on up to plus minus 1 whole power r into rc r minus 1. See here, we are starts from a simple concept. What is that? N of A union B equal to n of A plus n of B minus n of A intersection B. With the help of the tool, we are solving so many applications of the permutations and combinations like derangements and distribution of that different things to the different persons or different boxes, like that. See this problem. Find the number of ways in which 5 distinct balls can be distributed to the 3 different boxes if no box remains empty. Same concept. This is also asked in previous JEE mains or advanced. Here r is equals to 3 and n is equals to 5. From the above formula, the required number of ways, no need to explain each and everything. Already we discussed the derivation. 3 power 5 minus 3c1 into 3 minus 1 whole to the power of 5 plus 3c2 into 3 minus 2 whole to the power of 5. You may solve this problem by using another methods, but we are discussing today inclusion and exclusion concept. That is why I am choosing the method. 3 power 5 minus 3c1 into 3 minus 1 whole to the power of 5 plus 3c2 into 3 minus 2 whole power 5. On simplifying, we get 243 minus 96 plus 3. It is nothing but I think 150. So 243 minus 93, that is 150. These are the number of required ways such that 5 distinct balls are distributed to the 3 different boxes. So we are distributing the balls to boxes. How many balls are there? 5 balls. How many boxes are there? 3 boxes. So total minus 3c1. We are choosing one empty box and send the remaining send the balls to the remaining boxes. How many boxes are there? 3 minus 1 boxes. We are keep one box as empty. There are 2 boxes are available. Send them to 5. Send the 5 balls to these 2 boxes in 2 power 5 ways. Keep 2 boxes are empty. This can be done in 3c2 ways. We have one box ready to take the balls. This can be done in 1 power 5 ways. Am I correct or not? This is 3 power 5. All possibilities. All the possibilities. The first box, the first ball maybe goes to 3 ways. Second ball may go to 3 ways. 3 different boxes. That is why 3 ways, 3 power 5 ways. So total number of ways is 3 power 5 minus 3c1 into 3 minus 1 whole power 5 plus 3c2 into 3 minus 2 whole to the power of 5. So 243 minus 96 plus 3, that is 150. The number of required ways is 150. So in this manner we can deal the 2 different things like derangements and as well as the distribution of things, different things to the different persons or different boxes by using the inclusion and exclusion concept. Okay, thank you.